All right, we are recording. Hello, hello, hello. I am Mr. Forbes. As you can see, hopefully this is working out here. I did not have a chance to get to the smart board at school to record, so we were having to record a lesson at home, and I use this Streamlabs technology at home. The cool thing about doing this, though, is you're going to see my little face in the corner as I'm teaching. So I'm looking kind of awkward, but whatever. The downside is you're going to see me doing these lame PowerPoints. So it's okay. I know my handwriting's awful on this, but we're going to get through it together. So let's do this. I just realized that that's ugly. And that's kind of ugly. So that's not good. Oh well. Sometimes when I transfer the notes from like Smartboard to here, it cuts some of them off. So I'm just seeing which ones just got off. Okay, nothing too terrible. I can just rewrite those. Today's notes. So we talked about yesterday or the last time we met. We talked about doing algebra with limits to solve them. Okay, whenever we have a hole or asymptote that prevents us from actually just plugging in the limit. In today's notes, we're going to just continue with that with some examples. Some I may do, some I may save for class. We'll just see how time goes. Talk about one extra little concept today, something called squeeze theorem that kind of goes with limits. It's kind of the first, honestly, the first real calculus topic that we're going to learn. I mean, limits and tangent value or average rate of change, we've seen that before, but the squeeze theorem is the first official theorem or something new of calculus that we're going to learn. So that's kind of cool. All right, well, let's just try some of these problems, see what we can remember. H. Okay, well, if I plug H in, obviously we get 0, so that doesn't work. Okay, so in this particular example, and I want you to pay close attention to this problem right here because you're going to see this type of limit show up later on in the future with derivatives. But anyway, how this is solved, we got to get H away, so maybe let's try to simplify the top out. Let's see what happens if we do that. So that would be H, and I should write limit H approaches 0 of H squared plus, is that 2AH plus A squared minus A squared all over H. Okay, all I did was factor the top out or FOIL the top out, and now I'm going to combine like terms. I noticed that the A's go away. And if you notice then when the A's go away, I can take out a GCF of H on top. So I got H squared plus 2A now. And that should be just a singular H. I apologize. So H times H plus 2A all over H. And the H's cancel. So I'm left with the limit. H approaches 0 of H plus 2A. And if I plug 0 into that, I get 0 plus 2A, and my final answer being 2A. Okay, so that limit as I approach 0 simplifies down to 2A, whatever A value is. All right, so that was just doing a little bit of simplification. This next problem should look pretty similar to you. As far as how to approach it, if you notice on top here, okay, so first of all, I guess we should try plugging in pi over 3. If I plug in pi over 3 to cosine, I get 1/2. 1/2 of 2 is 1, and 1 minus 1 is 0. So it makes the denominator 0, so maybe it's a whole. Well, if you notice on top, we have something that looks pretty similar to 2x squared plus 3x minus 2. Like, those two look very similar, and they factor the same way. So if you feel good about factoring the top, you can factor the bottom. And you can do bottoms up, you can do whatever method you want. And if you have trouble with factoring it, we can talk about it later. But it does factor to 2 cosine x minus 1 and cosine of x plus 2 all over 2 cosine x minus 1. We still got the limit as x approaches pi over 3. Okay. All right, cool. So now you notice that bad boy that made my denominator 0 cancels out, and I'm simply left with the limit x approaches pi over 3 of cosine of x plus 2, which if I plugged pi over 3 to that, again, you get 1/2 plus 2, which is equal to 2.5, or I guess 5/2. right, there you go. First two problems down. Finito. Let's try this next one. All right. This next one looks pretty similar as well. We got another complex fraction example. I plug 0 in, it obviously makes the denominator 0, so we got to simplify it. And the best way with complex fractions is to multiply by that LCD, all right, which in this case looks to be 4h plus 2 squared. 4h plus 2 squared. And I'm going to multiply that through the tops of each of these fractions. So if I multiply to that first fraction, the h plus 2 squareds cancel out, and I'm left with 4. And then minus, in the second fraction, the 4's cancel out. So I'm left with h plus 2 quantity squared. And then on bottom, nothing cancels out, so I'm just left with 4h, h plus 2 quantity squared. And I'm still taking the limit. All right. I encourage you to pause the video, see if you can get the rest on your own. I mean, keep trying these on your own before you watch the video. I really suggest that a lot. But we're still trying to factor out that h on bottom so we can take the limit. Let's simplify the top. Okay. So let's see. We got the limit. H approaches 0. The top's going to simplify to 4 minus, and then in parentheses, h squared plus 4h minus 4. All over 4h, and I'm going to leave that bottom part unsimplified out because I'm trying to get rid of this h right here. So we're going to try to keep that in factored form as much as possible. Okay. All right. So then we got let's see. So we got the limit h approaches 0. What happens is, well, it looks like that we got. Oh, and I apologize. This should be. I don't know why I put minus 4. It should be plus 4 right there. So then we got the 4 minus the 4 on top, and we're left with negative h squared minus 4h all over 4h, h plus 2 quantity squared. And then it looks like we take an h out. So we're going to do the limit. H approaches 0. I'm going to take that h out on top. So we'll take that h out, and I'm left with, looks like negative h plus 4. Negative h. Oh, I'm sorry, minus 4. Why did I say plus 4? Minus 4 all over 4h, h plus 2 squared. Okay. And now you notice that we have it in factored form that this h and this h cancel out. So, with that being said, I'm able to actually plug in 0 now with those factors canceled out. So I'm going to go ahead and plug in 0. It's going to be negative 0 minus 4 over 4 times 0 plus 2 squared, which ends up being what? Negative 4 over 2 times 2 is 6, so 16, or negative 1/4. There you have it. It wasn't too bad. Come on now. Let's try this one. All right. Now, maybe pause it, try it on your own, do what you want to do. But something I want us to try here. Cosine x minus 1 over sine. So if I plug 0 in, sine of 0 is 0, and it doesn't work out. Okay, so we have to try to simplify it a little bit. Okay. Well, usually I would encourage you to try to substitute something in, like a substitution for cosine or sine, but there really is nothing. I mean, if it was cosine squared or sine squared, we could use the Pythagorean identity, but there's really not much more we can do. Okay. Well, what I want us to recognize here is this is just a little stretch, but something that happens whenever you can't simplify out with like trig IDs is you can treat this like a conjugate pair. You can actually multiply the top by cosine of x plus 1 and the bottom by cosine of x plus 1. So that's definitely a strategy to try if like no trig IDs work. If you see a binomial with trig, maybe try to do the conjugate pair. So then on top we have the limit x approaches 0. It's going to be, if I FOIL the top part out, the middle terms cancel, and I got cosine squared x. It'll be minus cosine plus cosine, and that cancels. but then minus 1 all over cosine of x plus 1 times sine of x. Sorry, the handwriting is god-awful. I really do apologize. But cool, the idea is we're trying to get rid of that sign, and if you notice right here, now I have cosine squared. Now maybe it would be probably a good idea to try to do Pythagorean identity. So I could say like the limit as x is approaching 0, this would actually be cosine squared is the same thing as 1 minus sine squared x. That is just the Pythagorean identity. Minus 1 all over. And then we got sine of x times cosine of x plus 1. Now here's the cool thing. 1 and negative 1 go away. So on top I have negative sine squared x, and on bottom I have sine x in factored form. So I can actually cancel this sign out with one of these signs. So what I'm left with is the limit x approaches 0 of negative sine of x on top, and on bottom I'm left with cosine of x plus 1. And I can plug 0 into that, and I can get the limit. So 0 may not work in the original function, but it must be a whole that can work in the other function. So that's negative sine of 0 over cosine of 0 plus 1. Which in this case the sine of 0 is 0. And the cosine of 0 is, let's see, 1 plus 1. So in this case, it's just 0. All right. So, not too bad for those 4 problems. Let's try 2 more, and then we'll move on. All right, so now right here, another example. Again, I'm going to 0. If I try to plug in 0, it doesn't work, so I got to do something to simplify that 0 out. Okay. Now here's the cool thing. You probably recognized already. We have a binomial. All right, that minus right there, and we have 2 radicals in the binomial. So I'm sure you're probably thinking it's a little bit harder because we're only used to dealing with 1 radical, and usually 1 quantity in that radical. But this is another example of conjugate pairs. So 1 plus x plus the square root of 1 minus x over the square root of 1 plus x plus the square root of 1 minus x. And if you multiply that out, hopefully good things will happen. Okay, so I got the limit. X approaches 0. Now on top, I'm doing this term times this term. Now remember the point of conjugate pairs. So we're going to do first with first. The square root of 1 plus x times the square root of 1 plus x is going to be 1 plus x. Okay. Now then the middle terms actually cancel out because we're going to have the positive and the negative of the same quantity, right? You can even show that in your work if you want to, but those terms are going to cancel out. And then I'm going to be left with minus, and then the last 2 terms multiplied together is just going to cancel the square roots. So really, that is what I'm left with on top. And on bottom I have x, and then square root of 1 plus x, plus the square root of 1 minus x. So conjugate pairs with your best friend here. And you're going to notice some nice things happen for us. So 1 minus 1 goes away, and I'm left with x minus negative x on top, which is just going to be 2x. So I got the limit x approaches 0 of 2x on top, and on bottom I have x times the square root of 1 plus x plus the square root of 1 minus x. And lo and behold, my x's cancel. And so that factor that normally made the denominator 0 goes away, so I can plug in 0 and figure out the answer. It's going to be 2 over, plug 0 into that, it's going to be the square root of 1 plus, well, the square root of 1. Or 1 plus 1, which is 2, and that equals 1. So conjugate pairs, not bad. All right, and then in this last example right here, we got the limit as x is approaching 27. Okay, so if I plug 27 into that, you actually get 0 on the denominator, so you can't just directly substitute it in. Now, this is an interesting problem. We're trying to factor out this with something on top. Okay, What you may notice is that this, the x to the 1/3 power, that's the cube root of x. And 3 right here is the cube root of 27. That's an interesting concept. You're not used to viewing it this way, but if I want to factor out something on top with something on bottom, there is a way I can get this bottom factor from the top. And it's using the difference of cubes. All right, let's do the difference of cubes factor. If I took the cube root of each term, that would be x to the 1/3, and the cube root of 27 is 3. So we're using that formula a cubed, all right, I guess in this case is minus b cubed equals a minus b times a squared plus ab plus b squared. We're using that factor here, but we're used to dealing with like a nicer version of that, but we can still write that same factor this way. We got 1 over or x to the 1/3 power minus 3. We're going to put, and now it's a squared, okay? Well, what is a squared in this case? What is x to the 1/3 power squared? Well, that's going to be x to the 2/3 power squared. Okay, we're just squaring a third, and when I multiply, it'll be 2/3. Minus, or in this case, plus 2ab, or not 2ab, just ab. That's going to be 3x to the 1/3. Okay, and then finally, plus b squared will be plus 9. And on bottom, I'm left with x to the 1/3 minus 3. So I did difference of cubes to factor out the top there, and those bad boys are going to go away. So what I'm left with is the limit x approaches 27, all right, of x to the 2/3 plus 3x to the 1/3 plus 9, and I can plug 27 into that. All right, so 27 to the 2/3 power, that would be like taking the cube root and then squaring. So the cube root of 27 is 3, 3 squared is 9, plus 3 times the cube root of 27 is 3, and then plus 9, so that equals 27. All right. So again, pause that video, look back over those problems, see if you can do them on your own. And that's enough practice of algebraic stuff right now. Okay. All right, now I want to learn a new concept. Okay, and I'll explain and go over more detail with this in class, but I would really like to explain our first kind of official theorem here in calculus. It's kind of an interesting topic. It includes limits. That's why we're talking about it now. All right. So let's paint a picture here. Let's kind of set the scene. Let's kind of give us some common knowns that we have to have in order to do this. So it says, all right, what if we have an equation f of x that is less than or equal to g of x when x is near a? Okay, and except maybe possibly at a, but we're going to assume that it's always going to be less than or equal to g of x when x is near a, and a is just some value. Okay, and the limits of f and g both exist as x approaches a. Then the following would be true, right? It says that the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. That's not the theorem yet. That's just common sense. If the function is always less than the other function, if f is always less than g, then the limit is always going to be less than the limit for g. That's just common sense. Let me give you a graph to explain it. Here's a. Let's say we got this function g of x. Well, according to my criteria, f of x, we'll call it this function right here, is always less than g of x around a. So then naturally, if that's the case, whether it's continuous or not, the fact is that the limit here and the limit here are also going to follow that same inequality. That just makes sense, right? That's not the theorem yet. But if that's true, that's the criteria here, then this is the case. Okay. If f of x is less than or equal to g of x, less than or equal to h of x. So if we have three functions, all right, one less than the other, when x is near a, except possibly at a, then the following is true. Oh, well. And the limit of f of x is equal to the limit of h of x. So if these two limits right here are equal to each other at a, they equal some number L, then by the squeeze theorem, since this function is in between both of them, then it has to also equal the same limit. If the lower function and the higher function both are the same limit by the squeeze theorem, think about a sandwich squeezing that g of x in the middle of them, g of x also has to be the same thing. Let me show it graphically. Okay, so here's let's say here's a, and here's f of x. Okay, now we also have h of x, and h of x is bigger than f of x for every value of x except maybe at a. Okay, let's say we have that right there as h of x. The reason I made them touch at a is because their limits are equal. Okay, their limits are equal. Then if we have some function g of x that is bounded by those two functions that's in between them, it is squeezed. All right, think of it literally squeezing. It has to also converge to the same exact limit. All right, there's no way, especially if it's in between the two. Okay, if it's in between the two, then the other two, max and min, meet at the same point. Then g of x also has to have the same limit there. All right, they all have to meet there. That's the squeeze theorem. So if g of x is squeezed between f of x and h of x near x equals a, and if f of x and h of x have the same limit at a, then g of x is forced to also have that same limit. Now, we're going to use this idea. All right, we're going to use this idea because the idea is whenever we're doing this, like g of x is going to be the function given to us in the problem. And we need to figure out its limit. And sometimes we're not going to be able to use our limit rules to figure it out. So we're going to have to create h of x and f of x with known shared limits to figure out the value of g of x. Let's look at an example. It says, use the squeeze theorem to evaluate the limit. And this part is what got cut off at the beginning. But the problem you'll have on your notes says the limit x approaches 0 of x squared sine of 1 over x, and that's it. Now, if you try to plug 0 into that, it's going to be undefined. You can't do 1 over 0. Okay? Now, this right here is my g of x. Okay? Now, you use squeeze theorem. Let me just go ahead and tell you. In calculus, the only time we ever use squeeze theorem is when we have trig. All right, whenever we're doing sine and cosine, and I'll tell you why. Okay? So we can't figure out this limit by doing any simplification or crossing things out or algebraic expressions. But what I can do is I can build this function. Okay, I can build this limit, and this is how. All right, we're going to create this inequality. We're going to create f of x less than or equal to g of x, which is what I'm given, less than or equal to h of x. And this is how. We're going to start off with the fact. We're going to start off with what we know. We know an inequality already. We know that sine of x is less than or equal to negative 1, less than or equal to positive 1. That's why this is so useful with trig, because we know an initial inequality. We know that the output of sine of x is always going to oscillate between negative 1 and 1. That is its domain. Its domain is negative 1 to 1, so keep that in mind. That's how we start this function up. Now, it's not what we started with, but the squeeze theorem says let's build up to that. Okay? So, we're going to show this in steps. All right, we started off with doing the sine of x. Okay? Let's now add the next piece, which is going to be the sine of 1 over x. Okay? Now, if I do the sine of 1 over x, and I usually just start off at this step, because no matter what input I put into sine, that's not going to change this part of the inequality. No matter what I put into sine, no matter what I change up in sine, the output's always going to be between negative 1 and 1. The only time that changes is if I do operations on the outside of sine, like change the amplitude or change the midline. But inside the sine, that inequality is still going to be the same. Okay? So we've built up to that point. Now the only thing we're missing is this x squared. So the next part we're going to do is the x squared. Now this is going to change the inequality. Okay? So if I multiply the inside here by x squared, I am changing that inequality between -1 and 1. And what I'm doing is if I multiply the inside by x squared, I got to also multiply the outside by x squared. So now that inequality is true from what I've started with, from what I know. Now we're almost created this entire function. We got everything inside the limit. Now let's tack on the limit. Okay, so we're going to do the limit part now. So we're going to say the limit as x approaches 0 of -x squared less than or equal to the limit x approaches 0 of x squared sine of 1 over x less than or equal to the limit x approaches 0 of x squared. Now, based off purely what we knew at the very beginning and us building up to what we started with, we now know that this inequality is true. We now know that this is what we started with, and it is between this inequality and this inequality. The whole point I did that is I can take the limit of this and I can take the limit of this. You just simply plug in 0 for x. It works. It's defined. The limit as x approaches 0 of -x squared is -0 squared, which is 0. The limit as x approaches 0 of x squared is just 0. Like, I can plug those values in. And I know that this is true. So I chose a smaller function f of x, I created a smaller function h of x, and I showed that g of x is squeezed to have the same exact limit as them. And this is most helpful for trig functions when you can't simplify. So what we can say right there is therefore, this little symbol right here means therefore, those 3 dots. Therefore, by squeeze, did I spell squeeze right? Yeah. By squeeze theorem, then you want to write the whole thing again. The limit as x approaches 0 of x squared sine of 1 over x also must equal 0. Pretty good, huh? Squeeze theorem. It's not bad. It's actually pretty straightforward once you get the hang of it. Now I'm going to try to do one more example. I'm getting to my 30-minute mark, but I think I might have time to do this. And we'll also do this in class tomorrow. Maybe I'll get you started on this and I'll give you time to try it on your own and you can look over the notes and check it, but I'll definitely go over it tomorrow. Here we got the limit as x is approaching 0 from the right of x to the 1/2 e sine to the pi over x, boom. Now this is a crazy mess, but if I plug 0 into this, and the reason it's specifying 0 from the right, well, there's really no reason actually, to be honest with you. So you can choose to do it however you want. I mean, the fact that plus there doesn't mean anything, so don't stress about that. Okay, but I'll get you started on it. What I want you to do is I want you to start with doing the sine of x between -1 and +1. That's what we know. Now, try to build this function all the way up to the limit starting with sine of x. I'll give you a hint. The next thing you need to do is sine of pi over x, and then you want to raise everything to the power of e. Raise e to the power of it. And keep building from that. See what you can do. Alright, and we'll finish this tomorrow in class. You guys have done amazing today. I love you all always. I'm right at 29 minutes and 54 seconds. I got to stop right at 30 minutes. 4, 3, 2, 1.